Hi, welcome to Pico Technology. My name is Barney Donahue. I work here as an automotive applications specialist, and today we're going to take you through a practical Pico session on CAN bus testing. I'm going to start the proceedings. We're going to look at different ways to connect to a CAN bus network, and then after that I'll start introducing some faults onto the network, and we can see how those affect the waveforms that you're going to see on your PicoScope screen.
My name's Steve Smith, and my role is to look at serial decoding within PicoScope. It's about looking at each and individual field within a frame, looking at the tools at your disposal, and hopefully demystifying a lot of CAN.
Lovely. So we'll begin by looking at the different ways we can connect to a vehicle. So in this part of the presentation, we're going to look at different connection methods and different ways you can access your CAN bus. So in the first method, we're going to use a pinout at the diagnostic link connector. In the second method, we're going to connect at the same place at the diagnostic link connector, but we're going to use a breakout box. And then in addition, in this video, we're going to show you how to connect directly at an ABS control module. And you might need to do this because not all vehicles give you direct access to your CAN buses at your diagnostic link connector. So the first thing we're going to do is connect up our scope. So we're going to connect our blue test lead to channel A and our red test lead to channel B. So now our test leads are connected to the scope. We're going to connect the two earth fly leads together and add a breakout lead. Then we'll add breakout lead to channel A and to channel B. So we're now ready to pin out at the connector. Okay, so we're down here at the diagnostic link connector, which is the white connector on the edge of your screen. I'm going to connect our three terminals. So we want our earth first, which we'll put on terminal 5. So there's number 5 on the top. Then I'll put CAN high, terminal number 6 next to it. And then directly opposite that, we've got our CAN low on terminal 14. Which an easy way to get to that is we've got 16, 15, 14 from the top at the back. Okay, so we're all set with our test leads connected to our diagnostic link connector via the breakout leads. We've got CAN high in pin 6 and CAN low in pin 14, and then our earth connection in pin 5. We're all sorted there. So the next thing we need to do is set up the scope. To allow for noise, we're going to put plus or minus 10 volts on each channel, on channel A and channel B. We've got 50 microseconds per division and 1 megasamples across the screen, which should give us a nice horizontal resolution so we can see plenty of detail. So next thing we need to do, we can just start the scope. Lovely, that's running, and we'll turn on the ignition. And there we go, lovely. We've got a perfect CAN bus signal on the screen. So we've got CAN high going from 2.5 volts up to 3.5 volts, and CAN low going from 2.5 volts down to 1.5 volts. Perfect. In our next connection example, we're going to use a 16-pin breakout box to connect to our diagnostic link connector. So let's do that. Very simply, we take the extension cable and plug that straight in. And you can see that it lights up. We've got a couple of lights of interest here. We've got on pin 16 a battery positive supply being indicated. Same on pin 5, we've got a ground connection indicated. And depending on whether the ignition's on and off, we will get different buses active as well. Let's connect our scope into our breakout box. We take our test leads Again, we've got our earth fly leads joined together, and we need to use some adapters actually here to get our ×1 test leads into the breakout box, and we'll add those, and we'll put, so you've got channel A, if you remember, is CAN high, so that goes in pin 6. Channel B is CAN low, so that goes in 14. And we can put our earth fly leads in either ground, 4 or 5, equally okay. So that's all connected. So again, we'll start the scope and we'll turn on the ignition. And straight away, again, we can see just as before, we've got our high and low signals as if we were connecting at the pins like we did before. Lovely. Okay, so now we know 2 different ways that we can connect at the diagnostic link connector. And in our next part of our presentation, where we're going to start look at actual testing for CAN bus faults, you'll see a method using backpinning of how we can connect to a high-speed CAN bus at an ABS control module. Right, before we start to look at any waveforms on the screen to look at our CAN bus health and possible faults, first thing we're going to do is just do a quick CAN bus health check. And to do that, we're going to look at the resistance between the CAN high and the CAN low lines. So if you remember, our CAN bus circuit is effectively a parallel circuit on this high-speed network. So we've got 120 ohm resistor at one end in an ECU and another 120 ohm resistor at the other end. So when we look at the total resistance between the high and low levels, we get a total resistance of 60 ohms. So that's what we expect to see. If we don't see that, then that's telling us that maybe we've got a high resistance, an open circuit, or a faulty termination, and we need to look further. Right, before we connect up and do that, 2 things to remember. Firstly, switch off your ignition and take the key out. Secondly, disconnect your battery. I've already done that, so we're good to go, and we're going to look at the total resistance with everything connected up first. So we take the 2 pins that we looked at before, the CAN and high load lines on the ABS circuit. So we got CAN high on 15, CAN low on 11. Might be vice versa, but that's okay in this case. And again, back probing just for convenience here, making sure we're not damaging any seals or shielding. And with those in place, all I need to do is get our digital multimeter and look at the resistance. Waiting for it. There we go. And we're at 61.7/8 ohms there. So that's lovely. That's exactly what we expect, and that's good. Say it wasn't good, what you weren't expecting, then next thing we could look at is the termination resistors at each end. So to do that, if we take out the backpinning probes, we can disconnect the ABS module, and there we go. Knowing that we've got 1 termination resistor in the module and another resistor at the other end of the line somewhere, we're well placed to check for the resistances at the 2 ends. So again, we'll use breakout leads for convenience. So I'll look at the ABS control module first. So bear with me whilst I get these probes in place, or these connectors in place. Right, lovely. That's the first one in. So that's 15. Now we go to 14, 13, 12, 11. There she is. Double check. 15, 14, 13, 12, 15, 14, 13, 12, 11. Lovely. Okay, so now if we look at the resistance down the end of those two on our ohm meter, right, what are we getting? There we go, so 126 ohms, so lovely, that's exactly what we'd expect. And so that's proving that we've got the termination resistor in the ABS control module. Now if we look down the whole bus, again finding the same pin, so 15 there. On this side of the connector, so 15, 14, 13, 12, 11. Marvellous. Take our digital multimeter. Look at that. What do we get? Again, 120 ohms. So perfect. So we can safely say that we've got the correct terminating resistances in the CAN bus circuit, and that there are no faults on it at present. In this part of the presentation, we're going to look at the common faults that you might find on a CAN bus network and how they affect the waveforms that you see on your screen. For example, there might be shorts to battery positive, battery negative, short from CAN high to CAN low, open termination resistors or open circuits generally, all those types of things. On this vehicle, we've got a ABS control module, really nice and available close at hand here. That will give us access to the high-speed CAN network, and on that we'll have the engine control module, ABS control module, instrument cluster, if it's got it, a transmission control module, and even adaptive headlamp modules, plus of course a steering angle sensor. So plenty we can look at. We can use the same settings that we've already described in PicoScope, so we can just load up the settings from the physical layer guided test. That's all good. We've got PicoScope channel A and channel B connected as before, and now all we need to do is connect our probes. So back to the same connections, no different. We've got our earth fly leads. Again, we've got a lovely earth connection available right at our fingertips, and now we've got we need to back pin on the ABS control module. Obviously there'll be a lot of breakout leads involved otherwise, so we'll back pin. We can do CAN high, which we can put straight into pin 11. Now obviously when you do this you have to be very careful not to damage any seals or damage the shielding on the wires. And then on pin 15 we've got CAN low, so you just slide that in there gently, make sure we've got a good connection. Lovely. So we've got earths connected, CAN high, CAN low, PicoScope connected. Now all we need to do is start the scope, so that's waiting for data, and we start the engine. There we go. So we can see we've already got a lovely normal CAN signal at the moment, and we know at this present moment this vehicle is functioning as it should. So let's start to look at some different faults that we might see on a day-to-day basis in your workshops. So the scope's already set up and we're going to start it running, and now it's waiting for data. We'll turn the ignition on. There we go. So the first thing we're going to look at is a short to battery positive. So we'll introduce the fault and look at the change in the waveform. Right, so we see immediately that the waveform or the channel is overranging. So if we change to 20 volt range on channel A, now we can see that the CAN high has gone up to battery voltage as we'd expect. Now we'll have a look at the CAN channel B, and we can see that the CAN low is also being dragged high with the CAN high. So they're both being dragged up towards battery positive. But what you must notice is that we no longer have any bus or messages present on the network. Now we're going to look at what happens when we short CAN high to battery earth. So we start the scope, as we're waiting for data, turn on the ignition, there we go, and we'll introduce the fault. As I say, it's going to be a short to battery negative, and we'll see what happens to our waveforms. Okay, so we can see immediately that both CAN high and CAN low have been pulled down to battery negative. Actually, because we've shorted on CAN high, it is at 0 volts. CAN low is just a little bit above that. But again, we can see that there are no messages actually present on the bus, on the network, although you can see from the spikes that the control units are attempting to communicate, but there is no communication at present. So we can see in both cases a short to battery positive or battery low. In either case, the whole network is destroyed by those faults. Our third short type fault is going to be a short of CAN high to CAN low, and we're going to see what happens to our waveforms in that case. So we'll start the scope and we'll turn on the ignition. So it's all operating normally, so we can see our messages. Now there we go, so we can see the fault's been introduced, and we've got both lines at 2.5 volts. So this means that our control units cannot drive the voltages apart from each other. It's a differential circuit, so they're connected to each other and they're remaining at 2.5 volts. And again, you can see that communication has been destroyed by this short type fault, as it was with the others. Okay. Now we're going to look at a different type of fault. We're going to look and see what might happen if we've got a termination resistor missing from our network, one of the two. So we're going to simulate this by removing the ABS control unit from our network, and we know that our ABS control unit has got a termination resistor in. So as you can see, we've started the scope and we're going to turn on the ignition. Now we've done that, you can see that there's some bouncing around in the signal. It's not quite as stable as it was. Little wavelets occurring here and there, and this is there we go, and this is symptomatic of a missing termination resistor. Remember, we've still got one in, so we've still got communication present on the network, and this is obviously a key difference between what we were seeing earlier with our shorts. We've still got communication, but for example, if you were going to do a resistance check on the network, you would find that it's only got a total resistance of 120 ohms rather than the 60 ohms that you might expect. So that's the effect of a termination resistor missing. Okay. So in our next example, we're going to look at what would happen if we had an open circuit on our CAN low line whilst we were measuring at a control unit. So in this case, at our ABS control unit. So we're measuring with the ABS at the ABS control unit. We're just going to collect some data. So we've got a normal signal, and now we'll introduce the open circuit. See what happens, and there we go. So now we can see that our high and low lines are doing exactly the same thing. So we've got a CAN high signal, and our CAN low signal is mirroring that, and that's because it's effectively connected to the CAN high line through the terminating resistor in the ABS control unit. So the network is still able to drive a signal. The other control units on the network are still able to drive a signal, but we happen to be measuring both of them in effect through the terminating resistor. Right, so we're going to introduce exactly the same fault again now, open circuit on CAN low, but this time we're going to be measuring at a location which doesn't have a terminating resistor, which has the effect of connecting CAN high to CAN low. So if we'll start up our scope, and we'll get our ignition on and get the normal waveform. So as you can see, it's all working normally here now. In a moment we'll introduce the fault, but what I want you to bear in mind is a moment ago we had the two signals mirroring each other when they were connected via terminating resistor, and now we see that CAN low has gone to 0 volts. We still have CAN high doing its thing, so we've got messages on the circuit, so the control units are still able to drive a message onto the bus. But at our measurement location now, we've got no messages making its way through to it or to our probe on the CAN low line. So now we can see how critical measurement location is in determining what the fault is. So the last fault we're going to look at in our network faults is the effect of our high resistance on CAN high. So we're going to introduce a 2.2 kilo ohm resistor into that circuit and see what the effect is. So we'll wait for some data. Okay, so we've got the normal messages appearing, and now we're going to introduce the resistance and see what happens. Right, so we can see immediately that our CAN high data is significantly distorted, so all the sharp transitions that you would normally observe have disappeared, so they've all become rounded off, and that's in both directions as it goes up to the high on CAN high and then back down to the 2.5 volts also on CAN high. So we would expect to see the same thing if we had a high resistance on CAN low, and so if you, for example, you had corrosion at a connector or terminals, then you could well expect to see both of your signals being distorted. But the key point is we've still got messages on the network. So quick summary: shorts destroy the network, high resistances don't, and open circuits might.
Welcome to the next part of our presentation, looking at serial decoding within PicoScope. Now this is going to look at connection to the vehicle, setup of the scope, application of serial decoding, math channels, and then just how much information can you pull out from serial decoding? What is there of real use to us as technicians? Can we decipher what computers are online? Just generally break the CAN down, demystify the whole CAN frame. So our setup process for connecting to the CAN network on this vehicle is via breakout leads that we've installed to the ABS ECU. So channel A, CAN high, channel B, CAN low, and then we'll reference to chassis ground directly at the battery negative terminal. Connectivity to this vehicle for measuring the CAN network, we have a breakout lead linked into the ABS ECU. So we'll use our Pico ×1 test leads. The blue is channel A, the red is channel B. Using our breakout lead, 4mm connectors on the end of our test leads into the convenient breakout lead, and then we can link the grounds together because they're both going to be referenced to battery negative, chassis ground. So we're all connected to the vehicle. We'll now set up PicoScope to look at the physical layer once again. We'll then apply maths to look at the differential voltage. We'll apply serial decoding and just look at how much detail is available in serial decoding. We'll use the export feature and the link file, and we'll also introduce not a fault, but we'll disconnect one of the ABS computers and export the data a second time and see if we can discover which IDs are missing from the network. Setting up PicoScope then for CAN analysis, CAN capture. We're going to go for quite a slow time frame, 200 millisecond divisions. That's going to give us 2 seconds across the screen, and we'll have this at 10 million samples. Now to see what that equates to in terms of sample rate, if we go to views, view properties, over here you can see we have 5 million samples per second, which is perfect for CAN. The voltage on CAN high is going to be 2.5 to 3.5. Now to allow for noise, we'll have this set to 10 volts. So channel A is going to be 10 volts, channel B is going to be 10 volts. We are on a ×1 probe on both of them. We won't use a trigger. we'll just leave this as free run. We've got here channels labelled up already, CAN bus high on A, CAN bus low on B. So yeah, we're ready to go. We press the start button, turn the ignition on, we'll capture CAN data. There we go. And that's moving at a steady pace across the screen that we can interpret rather than having it flashing up. I press pause and then I can navigate back through the buffer. There was first buffer and so on and so forth. So here we have our capture, CAN high, channel A, CAN low, channel B. This additional activity here, this is quite common. If we were to zoom in on this, you'll actually see there's ringing there. It's quite normal with the ×1 test leads. There we go. We could improve that. We could add the high impedance test leads. I think it's the TA375. But using a math channel, which we'll go through now, we can improve on this noise. And what the math channel will do, it will take away channel A from channel B, A minus B, which is the exact signal that the CAN controllers use. That is the physical layer. Differential voltage conversion. So if we go to Tools, Math Channels, and built into the software, you'll see there, A minus B. Click OK. Now you have a third channel that appears, and it has reduced some of that noise, but if we zoom in on there, this is the exact values that the computer is going to use to decipher what data is being transmitted. And the beauty of that then is that will provide us with the correct channel on which to activate serial decoding. So pull these waveforms up, just drag them out of the way, and now we go Tools, Serial Decoding, and Create. Now the network we're working on is CAN, and the data that we're going to decode is on A minus B. And it's tried to set this up automatically. We know that this A minus B will be 0.2 volt because 2.5 minus 2.5 is 0. 3.5 minus 1.5 is 2 volt, 0.2. So the best crossing point really is the midsection of the math channel here. That's 1 volt. We'll allow for a little bit of hysteresis on there. We'll bring that right the way down. That's just activity around the crossing point. We don't want that in any way to interfere with the decode. Now the baud rate, we know it's high-speed CAN, so that will be 500 kilo baud. We'll use the term CAN high on this, and we'll give it a name. And I'm going to say that this is the CAN network with the ABS on. In other words, the ABS ECU is connected. We're going to display the packets in the graph, so in the chart here, and also in a decode table. So click OK. OK once again. And there's our serial decoded data. Just drag that up so you can see a little bit more. And if we scroll down, the fact that all of that is in black means that that has decoded correctly, because if there had been any one of those packets or frames in red, we'd know that that was a decode error. So, for all intents and purposes, the information within the decode here is fine. Now I mentioned baud rate. If we just go back to settings here, we assumed a baud rate of 500 kilobaud, the speed, but we can calculate that. Basically, if we just zoom in on the smallest bit within a CAN frame, let's go here. That looks about right. What is that coming out at? Just over 2. Now let's go to this one here. There we are. The delta there, that is 2 microsecond. How does that translate? Well, bottom right hand corner here, frequency of the signal between those 2 points is just short of 500 kilohertz. You can see it there in the ruler legend. So we know the speed of this network. Had that been 250 kilobit per second, that would have come out at 250 here, and this would have been about 4 microseconds. Okay, so if we wanted to dig deeper into any message, I can click on here, and that will take me straight to packet 11 of the current buffer, and all the information that we need is there. Now, had we got a buffer which hadn't decoded correctly, let me see if I can find one and click on all buffers. So this is going to pull in all 4 buffers. We scroll down, we might be able to find one that is displayed in red. And would you know it, there isn't. Okay. Had there been, quite often what can happen is we lose half a CAN frame here because we've come to the end of the screenshot, and then it would flag up as red. But in this scenario, it's worked perfectly. Let's take a closer look then at packet number 11 in buffer 2. The recessive and dominant voltages. So you hear this term a lot with CAN. Our recessive voltage will be 2.5, and dominant will be 3.5 on CAN high, and then 1.5 on CAN low, and it's the difference between those two. Okay, so whenever we say dominant voltage, that will be when the bus is driven high and low, and recessive is when the bus voltage is in the rest state at 2.5. Now, how that translates in logic is that recessive is 1, dominant is 0. Okay. So let's have a look at the CAN frame in more data. Just to highlight another feature here quickly is if you hover over the CAN frame, there's a summary of basically what you can see in the decode table, so the start time, the ID, etc. Let's have a look at timing. So number 11, packet number 11, start time 3.685 milliseconds and the end time 3.919, so we can qualify that. We'll put the time ruler at the start and one at the very end of this packet. Yeah, so we've got 3.6, yeah, we're not far away, 3.919 there. There's an extra button here called Statistics. You can add that to get a little bit more information about the information on the math channel. So the max voltage, bear in mind 0 to 2 volt, but obviously we are either spiking or end of messages. We're seeing that raised voltage there. Minimum voltage, peak to peak, and packet time. Yeah, packet time in this scenario is 234.2 microseconds. Well, we are 233 here. If we were to zoom in a bit closer, we could dig a little deeper there. Let's dig a little deeper into IDs now at this stage. So let's choose another ID. We'll go for 1AO, which I'll explain a little bit later on as to why. And let's zoom in a little bit more on this whole packet. So you may have heard the term 11-bit identifier, 11-bit and 29-bit. Well, the ID here is, the length of that is, as near as damn it, 22 microseconds. Well, remember, 1 bit is 2 microseconds, so 11-bit will be 22. So there are 11 bits within that ID, and the ID 1AO equates to a message content priority. And if we were to think about ABS at this stage, because that's what we're dealing with, a message from the ABS ECU would be high priority, hence it's a low value, a low number. Whether that has come from the ABS or not, we're not 100% sure at this stage, but there's features that we can explore, and there are a number of things that we can do on the vehicle that hopefully will reveal that ID. As we move along, you see these points here, they call these stuff bit. If I just scroll along here, you'll see that wherever we have 5 bits of the same level, so 5 dominant or 5 recessive, after every 5 bit of the same level, the CAN protocol ensures that it inserts a stuff bit of the opposite orientation. So if it's 5 recessive, then it will insert 1 dominant and vice versa. That is the CAN protocol. Moving on then, ID, RTR, that is a remote frame request. So that might be an ECU that is requesting feedback from a particular ECU on the network. And as you can see, they're all 0 at this point. So everything on here is a transmission. Because had one of those been set to 1 in the RTR column here, it would have suggested that the message content from an ECU is requesting information from another. FDF is flexible data rate. Well, in this case, it's all 0. This is for CAN FD, where we can change the speed, the baud rate for the data for the payload. This is a conventional 11-bit non-flexible data rate CAN. Here we have the data length. So if I remove statistics just to give us a little bit more room, and we can pull this out here, we can see that the data length here consists of 8 bytes of data. 1, 2, 3, 4, 5, 6, 7, 8. CRC, cyclic redundancy check, that's the CAN interface confirming that this data and the transmission of the data is correct. This is the acknowledge bit. These are all 0, that all nodes that require that information have confirmed that they've received and understood. This is confirming that the CRC is good, it's a valid check. Bit stuffing is all correct and in order. And then a summary here that this whole message content is valid and correct. IDE, that's IDE extension, that's reserved for future proofing of CAN for additional length to IDs. Looking at the decode table then, let's just run through all the options here. We can shortcut to the settings menu and make any amendments that we need to here. We perhaps may only want to decode data between the time rulers, so we actually select this icon or to check this box here. Okay, link file, we'll come to that later. Export data, we'll look at that right now. So there's an option to export all this in CSV format. So I will do that. I'll call this ABS connected, because the ABS ECU is connected at this point. We'll save this on the desktop in our test folder. Save that. View, there's an option here to choose what you'd like to see or whether you want to change the font size. Statistics, we looked at that earlier. How do you want to view the data? It may be that you want it in a binary format, decimal, or ASC, ASCII 2. Keep that as hex at this stage. All buffers or just the current buffer. Incidentally, because we've just exported the data, we've exported all buffers. The filter option here, this is very useful. If I were looking for just a particular ID, something like 1A0, so place the space in there, 1A0, there it will list just those IDs for us. fields. So we could search buffer number and show just buffers 1. Click next, and that will take us to buffer 1. So to exit out of the filter, we would delete buffer. And now to clear this field here, we have to go back to current buffer, which will clear that. And here, whilst we're on current buffer, this is buffer number 2 of 4. Let's just have a look at the amount of data packets. So in one buffer only, 3,653 CAN frames, messages, packets if you like, of data. So 3,653 in 2 seconds. Okay, so it just gives you an idea of the bus loading at that point, the amount of messages transmitted on the network. And of course this was taken with ignition on, engine off. So how that would increase, I think it's a worthy test. Right, so now we need to capture CAN data again, but this time we're going to do the same capture and decode, but with the ABS ECU disconnected. So the ABS ECU and all its associated IDs will then be offline. So as we mentioned, we now want to take the ABS ECU offline. So if we disconnect the ABS ECU, make sure that that cannot reconnect in any way. And now we can carry out the same measurements again, looking at the CAN data and export that data. And we should discover that there are missing IDs now from the network. It's important to note that if you're going to do this, ensure that the ECU that you are disconnecting does not contain a termination resistor. Okay, so our ABS ECU is now disconnected. We'll start PicoScope. The settings haven't changed, so you can see the software is waiting for data there. Nothing on A or B, high or low. Maths has got nothing to calculate. So if we can turn the ignition on now. And there's our data coming in. And you can see that the maths is working and the decode table is starting to populate. We'll capture, let's say, 5 buffers. We'll stop there. Let's go back to buffer 3. Just scroll down. We've got plenty of data there. Yeah, we are now at 2,629 messages. Still in 2 seconds of data, 2 seconds of screen time. Okay, so what we'll do here now is we'll export this data. Sorry, before we do that, we'll actually export all buffers. So that's going to be buffer 4, which is partial. 3 is complete, 2 is complete, 1 is complete. Export. Go back to the desktop, it's a test folder, and this is going to be ABS, I'll call this ABS off. So we can now analyze these Excel files and see if we can find missing IDs. Okay, so to recap where we are to this point, that we've exported a CAN decode table from the from the CAN network with the ABS ECU connected, and then the same again but with the ABS ECU disconnected. So theory has it that a number of IDs will be missing now, because remember, the ID contains information about messages and their priority, message content. For example, think about brake lights on, brake lights off. Most probably, and we have to be careful here, we can't make assumptions, that message would or could originate from the ABS ECU. So let's look at the Excel files. So we'll go to the test folder, and this is ABS connected. So you'll recognize this straight away. This is our decode table that we exported from PicoScope. And one of the things we can do, first of all, let's go to the ID column. And let's go to Data and Remove Duplicates. And we'll continue with the Selected Data Only, Remove Duplicates from column E, because we know a number of IDs will be repeated. Remember, there were over 3,000 messages with the ECU, ABS ECU connected per every 2 seconds. Okay, there's a warning here. 11,871 duplicate values were found and removed. 50 unique values remain. Okay. So if we scroll down, we should see 50. There they are. So let's copy those. Copy that. We'll place them in column Q. So those 50 unique IDs are all relevant to the IDs transmitted on the CAN network with every ECU online, especially the ABS. And to make life easier, let's put these in the correct order. So we'll go A to Z. So now they are in alphanumerical order. Okay. And at this point, we'll save the data. We'll save it back in the test folder. And we'll save it as an Excel workbook, because that protects all our functions that we've got going in there. And it's still called ABS Connected. Okay, let's minimize that and let's go back to ABS off. So this is the exported data that we took when we captured all the CAN traffic with the ABS ECU disconnected. So same procedure again. Column E as all our IDs. We'll go to Data and Duplicates with this with this current selection. Remove duplicates from column E, and 9,369 this time. 41 remain. That's interesting. So we've lost a number of IDs. We had 50 on the previous, and now we have 41. Let's copy that, move that across to Q, and then put them in alphanumerical order. We'll copy this now, and we'll now take this back to our ABS connected. Okay. So these are the IDs that were present with all ECUs online, and in this column now we'll paste all the IDs with the ABS ECU offline. So we see we are a number short there. It's placed the header actually at the bottom, ID. I think at this point it might be a good idea to actually say ABS was off, and on this column ID ABS on. Okay, let's just save that once more. Okay, so now what we want to do is reveal unique values that are in this column, because they will reveal the IDs that are missing from this column when the ABS ECU was disconnected. So for that we go Data, we'll go Home, Conditional Formatting, let me just highlight these two cells here, Conditional Formatting, and we'll go Duplicate Values. Okay, and Format Unique with light red fill. Click OK, and there we are. There we have our unique values. Those are the IDs that are now missing when we disconnected the ABS ECU. So ignore these are just the titles of the columns that have been placed at the foot of the column, not the head. Hold down the control key first, highlight the unique values. Copy those and paste them into column S. Okay, so there we have it. Those are our unique IDs of interest. These are our IDs that are missing since the ABS ECU was disconnected. So let's see how we can analyze this further. Returning to our captures now, ABS ECU is reconnected and we're gathering data as before. So all ECUs online, no faults, CAN high, channel A, CAN low, channel B, maths is in there as well, and the serial decode is functioning, as you can see. We've got a maximum of 4 buffers. This is because we are at 5 million samples a second with 10 million samples across the screen. Okay, so let's pause at this point. Let's go back to the buffer 3, which is a full buffer. Let's have a look at our IDs of interest. So 1A0, that was missing when we disconnected the ABS ECU. So let's filter for that. 1A0, and there they all are. And what's interesting here is if you scroll down, look at the data, the payload, you see that the only byte that changes is the N1. So it's numerical, alphabetical, back to numerical. And that continues. And that's with no input from the driver in any way. So the ignition is on. That byte is constantly changing. Okay. So how could we use this information at this stage? We could bring in another channel and see if we can promote change within the data here. So thoughts around brake pedal switch. So on channel C, I've connected to the brake pedal switch located just beneath the master cylinder. And if I were to run this now, so let the buffers fill up, the software now is just looking at ID 1A0. It's collecting other ones as well. If I just minimize this, you'll see far better the raw data. So here's our brake pedal at rest. So the plan is to operate the brake pedal a number of times and see if any of the events change, any of the data bytes change from ID 1A0. So let's go and do that. So let's stop that capture and just go back through the buffer. So here the brake pedal is at rest. This is brake pedal on, off, back on again here. And let's bring the decode table back. Here we have an error frame, so let's just click on that to see what that is. And let's just minimize. And the reason that frame is in error because it is incomplete. Maybe if I just zoom out a little bit more. Let's go back to that decode table. Go back to the error frame, which was the first one here. It's packet 1 in the current buffer. Right. So we didn't capture the whole frame. Hence it was incomplete. Okay, second one was fine. All right, so we're searching just for filter 1A0. And let's zoom back out. we know that in this area here, the brake pedal was pressed, so we're hoping to see a change in the data bytes here somewhere. So let's pull these rulers in and ask the software just to decode the data between those 2 points, where the brake light went from off to on, back to off again. To make an amendment, we just go back to the decode table and decode between the rulers. Click OK. So now we are filtering for ID 1AO, and we're looking for a change. Okay, so that seems to be the same. But there is a change here. We go from 4.0 on this byte here to 4.8, back to 4.0 again. And see if we can close in on that a little bit further. So let's just decode between the rulers. Let's come into this section here. So now we are only decoding this area here. If I just minimize the decode table, you can see that that is the only area that's being decoded now. All this area here is being ignored. Bring the table back. Yeah, 4.0 to 4.8. Yeah, that's at the point the brake pedal goes on. Yeah, it remains on. Let's pull this out here to there. So we go from 4.8, brake pedal on, to 4.0. And let's see if we can really narrow this down. Yeah, 4.0 is brake pedal off. 4.8. Yeah, so we see how the brake pedal has gone off at this point when we're measuring at the brake pedal switch at the master cylinder. If I just drag this out, yeah, let's just have a look at that in terms of time. So it was at approximately this point here where the message was transmitted for brake pedal off. So let's measure that time before it was transmitted. 20 milliseconds. Okay, so we're drilling right down here. We have some evidence now that 1AO is an ID from ABS, because when we press the brake pedal, we see that our byte 2 there goes from 4.8 to 4.0 and back from 4.0 to 4.8. Let me just check that it's the right way around. Yeah, it's 4.0 with brake pedal off, 4.8 with brake pedal on. So our next ID to filter on would be 1AC. So let's take a look at that. Filter 1AC. There we are, they're all listed there. But we're only interested in what happened here when the brake pedal went on. So let's just decode between the rulers. Let's go from here and here. Okay, so 1AC seems to have activity regardless. Let's just come back here. So before we switch the brake light on or press the brake pedal, we see how these change here, these bytes. These bytes change here as well with no input. Yeah. But keep your eye on this one here. This is 01 throughout. Okay. And we'll drag the cursor to here, and we go from 01 to 4.1. Let's pull that ruler out a bit more. And yeah, we are 01 here, brake pedal released. And then here, brake pedal pressed. We go to 4.1. So again, that is looking like ABS ECU, because we know this ID misses or is missing when we disconnect the ABS ECU. And also now we can promote a response in the payload when we press the brake pedal. And again, let's just see how fast this responds. If we decode right over here into this area, we are at 4101. 41. Yeah, so 01 is brake pedal off. Let's pull this out as carefully as we can. Yeah, we go from 41 to 01. Yeah, once again, 30 milliseconds. Yeah, even less, 20 milliseconds. So just decoding the data in that area there. Let's have a look. Just in that area there, those messages indicate a change in the payload. We try and move these out of the way. So from this point here to this point over here, let's put that in perspective, we go from 41 to 01. Yeah. And that span is 26 milliseconds. So because we've got this so refined now, let's just minimize this a little bit and come back out. And let's concentrate on a area clearly from brake pedal off to brake pedal on, because we know in that area there we force a change in the payload from ID 1AC and 1AO. 01 to 41. And 40 to 48. So let's have a look at other IDs. Finally then, looking at the other IDs that we've got, you can see here that I've started to populate the results. We know that 1AO, when the brake pedal was on, byte 2 changed, 1AC, byte 6 changed. I can tell you that 2AO, 3AO, 443, 4AO, nothing changes at all. This one here, 4A8, byte number 3, that does change. I'll just run you through that now. So filter 4A8. Lock the time rulers here. You can see by clicking on this icon we can lock the time rulers together. That byte number 3 changes to 54. 5E there as well, but when the brake pedal is off, that byte is always at 0. Just unlock that again. Brake pedal off is always at 0. Lock that when the brake pedal is on. Yeah, it's constantly changing there, that byte. Whether that's reporting a change in pressure, I'm not sure, because the byte is continually changing. Okay, so what does that tell us? We know that a total of 9 IDs are missing when the ABS ECU is disconnected. We know that the operation of the brake pedal forces a change to the data field in 3 IDs, 1AO, 1AC and 4A8. We know that ABS IDs have a high priority as well, because the lower the numerical value, the higher the priority, and we've got a 1AO and a 1AC. But then again, that doesn't rule out the remaining IDs at this stage, because all we've done to force a confession out of these IDs, if you like, is operate the brake pedal. It could be that ID 443 that was missing will change its state if we were to spin a wheel, for example. So it's not definitive, but it's all we've got at this stage. So what else could we do to help with these IDs, or to convince us further that 1AO, for example, stemmed from the ABS? Well, this forum post goes some way to answering those questions. So picoauto.com forum post, search for who said what, who is online. In fact, if I come back, you get the actual, there it is, yeah, topic 21680. And here then we've got a CAN ID that I was chasing. It was 197. This is the shift lever of a BMW Auto. And you can see that I have a current clamp connected to the CAN wire, one of the CAN wires, such that when I operate the parking switch, we see a change of state to one of the bytes within the CAN message, but also that the current ramps up. So we know that at that point in time, the shift lever, ID 197, was transmitting on the CAN line. So that's one possibility. The other one is to look at the electrical signature during the transmission of a CAN message. The values of the voltage have a characteristic which you can determine. You can measure the CAN frame voltage is dominant voltage. This is when the bus is driven to high and to low. You take that, you get the Modal value of those voltages, and that reveals an electrical signature about the transmitting ECU. Unique electrical signature from each CAN node. So basically what that is saying is that when a node is transmitting a message, the payload, the dominant voltages are typical to that ECU, to that control unit. And this final forum post, topic 21680, as I mentioned earlier, looks at this exact process. So if I just highlight this here, you'll see that we are looking at the dominant values for CAN high and dominant values for CAN low. During this period, only this node, this computer, is transmitting a message on the bus. So if we discover that electrical signature from that ECU by doing some calculations using deep measure, we can identify other ECUs with the same electrical signature, so we can start to group IDs together because we know we've got one AO and one AC that we believe is stemming from the same ECU. So if I just quickly move on down here. Yeah, this one looks at CAN high. These are deep measure values, and we're looking at the maximum voltage for CAN high here, 3.5. We find out the Modal value of that. If I scroll down again, you'll be able to see that process using Excel, because we'd export this data from deep measure now into Excel. We discover this unique value here for the CAN high voltage, and we do the same for CAN low. So we end up with two values, the Modal value for CAN high and for CAN low. And then in Excel we plot them against one another. Here's such a plot, and 197 was the shift lever with the BMW, but here I'd got 517 and 335 that I was interested in, and both of those, they're actually on top of one another. You can't quite see it in the graph there, but I assure you that they are. They have the same electrical signature based on this process of grabbing the dominant high Modal value and dominant low Modal value during message transmission. So it serves as another tool, if you like, to try and qualify that your ID or your IDs are stemming from the same source, using current to determine that it's that node, that computer that's transmitting the signal. And then, of course, the procedure that we've discussed by disconnecting the device, seeing if the ID goes missing, forcing the ID to change the message, change the data fields. For example, pressing the brake pedal forced ID 1AC to change one of the bytes in the data message. It's tough going, let's be honest, that PicoScope is not a serial decoder in the true sense of the word. It's not going to log streams of data, endless streams of data. We're limited really by the amount of buffers. I think we've got 3 here. Previous capture we had 4. That was about 8 seconds of data on over 12,000 messages. With that said, knowing that we have these features that we've described over the last sort of 15-20 minutes or so, you have a tool at your disposal that will help you identify, qualify, certainly enable you to try and decode, decipher a number of these IDs and perhaps some of the messages using a link file as well. So the link file I didn't discuss, I'll come to that in the next video. Looking now at the link file feature in our serial decoder, we're looking at the current buffer. This is all the data from the current buffer. No longer are we decoding between the rulers. Okay, so here we click on link and we would create a template. That's the first step. We'll put this on the desktop in the test folder and we'll call this link. So let's go to the desktop again. To our test folder, open up the link. Okay, so here we have our ID. Well, we are interested in 3 IDs that we have been able to confirm, or no, not confirm, that's the wrong word at this stage because there are additional tests to do, but we believe at this stage stem from ABS ECU. There was 1 AO, 1 AC, and 4A8. And the description of that would be ABS. 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 So close that. Okay. That's our previous Excel file that we used for filtering duplicates. Okay, back at the PicoScope screen, click on link, and now we want to open our link file. And that's the file that we've called link. Okay, and that is imported into this decode table, but now you see where 1AO was, or 1AC, 4A8, has been replaced with ABS. So we've now renamed, if you like, the IDs of interest, 1AO, 1AC, 4A8, as ABS. And they pop up twice here. We could also search for those as well if we wanted to. We could go ABS, and there they all are. Okay, so it's a very brief introduction to a link file application. It goes much, much deeper than that when you start converting this data into human readable data. Yeah, thanks for watching. That's been a heavy going video, I know, but I hope it helps, and take care. So I hope you found that useful. That's an overview of the serial decoding feature in PicoScope 6. There's a lot more information on the forum or on the website in the library section.
Okay, so thanks again from Steve and myself, and we'll see you again soon. Goodbye.